All right. Well, happy Friday, everybody. It's end of week 5, so we're halfway through the quarter now, and it's May. So I don't know. That's exciting. I think. But yeah, we have like 5 weeks of school left. 6 weeks, I guess, with finals. But then all of our friends on semester are like done this week, so it's a little bit envious, right? Okay. Well, anyway, let's talk about I guess the material today. So we have this generative model, and we talked about maximum likelihood estimation, and finding the parameters, the weights in our linear model to maximize the likelihood we found is equivalent to minimizing the sum of squared errors. We also talked a little bit about kind of like how much information we can get from our data with regards to those parameters, and that's reflected in our Fisher Information Index. And that basically tells us, what's the relationship between the data and how good your estimates can be, okay? And so if your data has certain characteristics and you are trying to estimate the model parameters, and so if we just think about the simplest linear regression model, okay, where you just have a slope and an intercept, okay, and we don't often think about this, but characteristics of your data kind of control, I guess give you certain amounts of information. Like, are you going to have a very precise estimate of what your slope is? Or depending on the data you have, maybe your slope estimate could be quite a bit off, okay? So if you have lots of information, we would expect our estimate of the slope to be very, very kind of precise. We estimate like 1.5, and we would expect the true value to be, very close to that, maybe 1.51, maybe 1.49, okay? In other cases, depending on the data that you have, maybe you estimate your parameter to be 1.5, but based on the data, that could be wildly off. The true value could be as low as like 0.7 or maybe as high as 2.2. And so, how much information do we have about our parameters? That's reflected in our Fisher information, and kind of extending beyond that, we can talk about, okay, well, once we have our parameters and then we, try to make predictions, how much variability will we have in our predictions, okay? And so this is coming from this section in our textbook, okay? And basically our new observations, our new prediction is going to be basically our estimated slope and intercept, or our model weights, okay? So again, just kind of a linear model where we're just multiplying W times X. We plug in our new values of X. So you're saying, okay, I've got this model. I don't know if we're talking about Olympic gold medal winning times. We could say, okay, what if we had Olympics in 1995? Okay, that's not an Olympic year, but if we were to have one then, what kind of race time would we have seen? And you would just kind of take your model prediction, multiply it by your X new, and you'd get some kind of value there. Okay, this would be your new thing. Okay, and then kind of the variation. Okay, the variance here, we'll take kind of our model variance and then also kind of multiply it by our new x values here. Okay, and in the middle we have an X transpose X inverse there. Okay. And so interestingly enough, as far as the variation goes here, there's no values of y or t here. It just depends only on the x, okay? And that feels a little bit strange, okay? So here we're just talking about kind of the model's noise parameter. Okay, so this part makes sense, right? So we're talking about if you're going to make a new prediction and the data you have has lots of noise, so you have a big sigma squared here, well, we would expect our predictions to kind of reflect that and also have, a lot of variation there, okay? But interestingly enough, the rest only depends on kind of like what our x values are, okay? And the actual value of what the actual values are in y or t or whatever, that actually doesn't play a role. And so I wanted to kind of take a closer look at this. Oh dear. I thought they fixed it, but I think something's just wrong with the connections. But anyway, I have this kind of drawn out here, and so we are going to say our observed x values are, so this is just a simple linear regression model, okay? And my observed x values will be, I've observed a value at 1, 2, and I've observed a value at 99 and 100, okay? And so this, and we're fitting a linear model, okay? And again, the actual values of y, like, it doesn't matter, okay? I don't have any actual values of y here. But we can kind of get an idea of how much variation we'll have in the predictions that we make, okay? And I'm just gonna assume, like, we're just gonna use a constant, like sigma squared will just be 1. So I'm just gonna focus on this part here, the x nu transpose, x transpose x inverse, and x nu. And so the part that factors in is basically the observed or the x values in our training data and what our new observation of x is here, okay? And so here are x values in our training data. Basically, I got a column of 1s for my, my intercept, and then my x values, I've got a value at 1, 2, 99, and 100. And then I'm gonna make a prediction. I'm gonna say, okay, if I observed a value at 1 and 2, and I observed a value at 99 and 100, and I wanna make a prediction at 50, then we will have very little variance, okay? This is the variance in our predictions, and it reflects kind of a small amount here, okay? So we're just assuming our model noise is 1, then I'm gonna have even less, okay? This number is smaller than sigma squared, okay? Sigma squared is 1, my variance is a quarter of that. And it's kind of reflected, and this is my junky drawing here, okay? But let's say, there's a true relationship, okay? And, we have noise, so that's what these red dots are. So perhaps my observed value for 1 and 2 are these dots here, but, we're allowing for some noise, okay? And then my observed values for 99 and 100 are up here, and we're also allowing for some noise. And so again, the question is, if I take a random sample and you take a random sample, and we both agree, like, we're going to take a measurement where x is 1 and x is 2 and x is 99 and x is 100. I get my measurement at x is 1, you get a measurement at x is 1, I get a measurement at x is 2, you get a measurement at x is 2. And our values are going to be different. I fit my linear regression line and you fit your linear regression line. And we could see our estimated lines, that's what these different colored lines are supposed to represent, are all going to look pretty similar, okay? And how much variation is there going to be at this new location at x equal to 50? There's going to be just a tiny bit of variation here, okay? Just a tiny bit of variation. And that's reflected kind of right here, that the amount of variation, is, x transpose, x nu transpose, x transpose x inverse, x nu, times, our sigma squared. And if our sigma squared is 1, the variation here is a lot smaller at 0.25, okay? But if let's say I take all 4 of my observations, okay, at like x is 1, x is 2, x is 3, and x is 4, okay? So my observations are all right here, and then our new observation is going to be at x is 100, okay? So this is kind of, this is like the fatal mistake in linear regression that you should have been told never to do. This is like, don't extrapolate, right? So well, for multiple reasons. Okay, one is because we don't know if the linear trend is going to hold, but another part is that you just have huge amounts of variation. So if your observed values of x are at x is 1, 2, 3, and 4, okay, and again, I take a random sample where my x values are 1, 2, 3, and 4, and you take a random sample where your values are x 1, 2, 3, and 4, you know, we're going to get different sample values. If we plug in a new observation at x is 100, okay, and again, we're just using the same thing, x new transpose times x transpose x inverse times x new, okay, the variation in our predictions is going to be this huge number, 1,900, okay, all right, you know, and the picture is kind of like this, okay? Again, we have random noise. Our values are at, you know, 1, 2, 3, 4, and based on you know, what random data points I get here, you know, you could imagine getting a fitted line that looks kind of like this, right? Like the purple line, okay? But we could also imagine a fitted line that ends up looking kind of like the yellow line. And when we drag it out to say the new value is at 100, we could see there's a huge amount of variation in what our prediction would be, okay? And again, I don't know, it's kind of, it is interesting that the only thing that really matters is how much noise there is here, okay? So it's just kind of like the amount of noise in our data, observed data, are sigma squared, and then kind of the values of x themselves. But what the actual y values themselves are don't really matter, okay? So it could be down here, it could, you know, we could shift the whole thing up, and it's just based on you know, how much kind of noise we're observing will affect what we have here. If you do the same kind of thing, and you have x is 97, 98, 99, 100, and you're kind of extrapolating in the same, extrapolating but now in the opposite direction, where your prediction's at 0, you still also have a huge amount of variation here. I don't think I drew that one, okay? But you know, it's just kind of the flip side, right? So if I just extrapolate in the other direction where you know, my observations are 97, 98, 99, 100, okay? But we're plugging in our new value around 0, that variation is also huge, okay? If, you know, but as soon as we have kind of points in between, or, you know, I extend this, so here I just have a point at 0, 50, 100, and 101, okay? Again, that pinches down what our prediction is going to be. So here I have an observation at 50. I'm going to make a new prediction at 50, okay? If I've got a 0 and 100, that pinches down, and so we have very little variance here, okay? Okay, so here I have this. I can remove this. I could remove this, right? And we would still expect just a tiny, the amount of variance here is a little bit bigger, but still pretty low, okay? So, and that makes sense. Do I have a picture here? Okay, yeah, so here I've got an observation at 0, an observation at 100, observation at 101, okay? Here I have an observation at 0, 100, and 101. And I'm trying to make a prediction at 50. Oh, I'm sorry. In this data set, I do have observations at 50, okay? And this is kind of what my fitted lines will look like. Here, I don't have an observation at 50, okay? But these are what my fitted lines will look like. And yeah, basically, in both cases, whether my original data included this point at 50, like the amount of variance in my prediction here is going to be quite low, okay? So I'm not too worried about this, right? So I've got 0, 50, 100, 101. My variance is pretty low, 0.273. Here, I get rid of that observation at 50. I have less data, so my variance goes up a tiny bit, but not dramatically so, 0.376. And that kind of makes sense. This piece of this data point isn't providing a ton of information regarding where my slope and intercept and where my prediction is going to be. Okay. But here's the neat thing. If I have a different model, okay, so this is like I'm just fitting straight lines. Okay, I'm just fitting a straight line here. If I have a different model where I decide, you know what, let's have a quadratic model here, okay? A quadratic. So now I have a column of ones for my intercept. I have a column for my linear term, and I'm going to have a column for my quadratic term. So basically, I'm going to have x is 0, and then I've got 0 squared, and then basically 50 and 50 squared, 100 and 100 squared, 101 and 101 squared, okay? And so here I'm going to pretend I've observed an observation at 50, and I'm going to try to make a prediction at 50, okay? And as we might expect, the amount of variance we get here is right around the amount of variance we had like this whole thing turns out to be something very close to 1, okay? And perhaps that's not surprising, okay? What would happen if I remove this data point right here? Okay, so I'm doing the same kind of thing. One is I've got 4 observations, 0, 50, 100, 101, okay? And then I'm going to do the same thing where I just remove this observation at 50. And now I'm going to have 0, 100, 101. And here I'm fitting a quadratic model, okay? If I remove it, the amount of variation is now this really, really, really huge number, okay? And I'm still doing the same thing. I'm trying to make a prediction at x equal to 50, okay? So what happened, okay? Because back here, I had 0, 50, 100, 101. I am fitting a linear model, and my prediction's at 0.2, my variance is here. I'm making a prediction at 50. Here I have 0, 100, 101. I removed that 50 observation at 50. I'm making a prediction at 50. My variance changed barely, okay? Here I've got same kind of thing. Observation 0, 50, 100, 101. I'm trying to make a prediction at 50. This is my variance, okay? I have observations at 0, 100, 101. I'm trying to make a prediction at 50, and now my variance is huge, okay? And the reason why this has jumped so much is because, yeah, now we have this quadratic model, and that allows our model to be more flexible. And so which data points we have actually play a big role in what kind of model we can fit, okay? So and again, the crazy thing is the actual y values don't matter. It's just, how much noise do we expect? And so if I have, I've got observations at 0, 100, 101, and observations at 50, and I'm fitting a quadratic model, like these are the kinds of lines that I can fit, okay? So if I have an observation at 50 and I've got some noise here, they're all gonna have to kind of run through here, and we're gonna kind of get these similar looking quadratic lines, okay? But if I have only an observation at 0, an observation at 100, and an observation at 101, okay, and I say fit a quadratic model here, okay? Basically, quadratic thing is just this kind of this parabola looking thing, And depending on what I have here and what I have here, these are kind of like the only two endpoints that are like, they're not like endpoints, but these are the only two parts that are like constrained to the data. The thing that fits in between could be wildly different, right? So we could imagine, you know, a data point here, a data point here, and here, and our best fitting quadratic thing will be this kind of this purple curve right here, okay? Or you can imagine, because of just the amount of noise, that the observation at 100 is a little bit higher than the observation at 101, and so and you have an observation down here at 0, and so therefore the best fitting quadratic line is going to be this green line here, okay? And so without the point in the middle at 50 here, okay, what our fitted lines could be, you know, varies quite a bit. And so here, you know, I'm trying to make a prediction at x new is 50, and it's all over the place. It's all over the place, okay? And I didn't put this into the notes, but if I say, well, you know, I don't want to make a prediction at 50, I want to make a prediction at 99, okay? If I want to make a prediction at 99, we would expect both the model over here and the model over here to have similar amounts of variance in the predictions, and that's what happens. And I think I have. I think I have that over here. Okay, so I did. So this is that's that one, and that's that one with the huge amount. But let me just kind of copy this. And I'm going to just say, hey, let's make a prediction at, say, 99, okay? So instead of 50, we're going to make a prediction at 99. And over here, we're going to have a prediction at 99. And what we would expect to see, mathematically, is like the amount of variance at 99 with the linear model is 0.46. And the amount of variance with our quadratic model, you know, it's bigger, 4.88, but it's not this dramatic jump to, you know, whatever it was earlier, 1200, okay? So, you know, right here, you know, at 99, we would expect, yeah, sure, more variance over here versus the linear, not the linear model. They're both quadratic models, but here, because, you know, we have a observation at 50 that kind of informs where it's going to be. You know, that shrinks down the amount of variance over here. We don't have an observation at 50, but so there's, you know, kind of a lot of noise here, okay? Yeah, putting an observation in between, like, if I don't put the observation at 50 over here and I put it at like 1, okay? You know, now we have a lot of variance, okay? So, yeah, it is kind of the amount of variance we get in our predictions depends on what observations came in our training data, okay, in our X, and that's part of this X transpose X inverse, okay, and where our new observation is going to be, our X new, okay, and it's you know, when you do this multiplication back here, like what your X new is compared to what your X transpose X inverse is, they either will kind of cancel, like, I don't want to say cancel each other out, but they'll multiply in such a way that the result is going to be really small, or they'll multiply in such a way where the result is going to be very large, okay? And the actual values of t or y don't actually factor, it's just where your X values are and how much noise you have in the original system. Okay, I forgot. What is my view quiz answer? Give me a second. Okay, so our first view quiz answer today is the letter C, C as in cat, and that's what we have there, C as in cat. Okay, so the textbook goes a little bit more into it. goes through the derivation of this part, and this is on variability in our predictions, kind of based on what we estimated our weights to be, and so this is reflected there. Okay. There's like 2 parts to our lecture today. The second part, now we're like doing something totally different. I don't know about totally different, but different, and we are going to introduce the multivariate normal distribution. Okay, as this is going to form kind of our base distribution for a lot of the methods that we'll look at in the future. So in the coming weeks, we'll look at some clustering, or actually first classification methods, and then I guess later clustering methods, and we will use the multivariate normal distribution. So I think you've already seen the multivariate normal distribution, but again, I just want to kind of make sure we have the same base and background, and so we'll review this and just kind of establish certain facts about the multivariate normal distribution before we go on. So we can think of the multivariate normal, or the multivariate Gaussian, or whatever we want to call it, as an extension of the univariate normal distribution. And so our univariate normal distribution, we're accustomed to seeing. We have mean mu, variance sigma squared. I guess some parameterizations just have the standard deviation sigma, but it's the same idea here. And our density is 1 over root 2 pi sigma squared. It's kind of completely unrelated, but there's a fascinating video on YouTube with 3 blue 1 brown talking about where this pi shows up, because it feels like totally like, why is there a pi in the middle of this normal distribution? Like, what does this have anything to do with circles? Because that's what we think about with pi, right? And it's actually 2 pi is the other tau, which might be the better thing, but anyway, like, it shows up there, and there's just kind of like this I don't know, serendipitous thing. This is like the thing about math, right? It's like where these things that seem totally unrelated just like somehow come together. And so, the e to the, exp and stuff, and pi, like these transcendental numbers. Anyway, recommend it if you've got like a spare 20 minutes. But okay, anyway, so this is our density function, e to the, whatever x minus our mean squared over 2 sigma squared, right? Okay. Now when we're dealing with the multivariate normal, okay, we're not talking about just one real number along the real number line, but now we have this higher dimensional thing. Okay, the easiest for us to visualize is like a 2-dimensional multivariate normal. Okay, because now we have a plane, and then we can add the 3rd dimension of what the density is, and we can visualize that. We can all visualize 3-dimensional things. We have a hard time visualizing anything higher, but it can be extended to higher dimensional vectors. But it's easy for us to just think about kind of a 2-dimensional case. Okay, and actually we have lots of pictures of the 2-dimensional. Yeah, so they look like, right? So this is one. Why is this so small? One lovely picture, right? It just kind of like looks like a hill. It's like you've taken the normal distribution and you've made you spun it around and made a hill. It doesn't necessarily have to look like a circle from the top. From the top, it can definitely look like an ellipse. But the idea here is, if you were to take the marginal distribution, like if you just took only the x values, it would look like a normal distribution. And if you looked at only the y values, the distribution of y values, that would also look like a normal distribution. And here there's covariance between x and y. And so you get these ellipse. The cloud of points looks like an ellipse. Looking at it from top down, if you had a density, right? So this is the red areas are taller and the blue areas are lower. So, your density would look something like this. And, when you plot it in 3 dimensions, looks kind of like a hill here. This one's a lot more, the elliptic nature of it is a lot more pronounced. And this one is, much more kind of round and circular there. But this is the multivariate normal. And here's lots of fun little pictures, right? Okay. And so we have this d-dimensional vector. I just showed you 2-dimensional ones, but we have these d-dimensional vectors, and our parameterization we would say the vector x comes from a normal distribution where we have the mean vector, I guess our mu vector, and then our variance, we have a variance matrix, okay, and that's going to be sigma, okay, and this is going to be a d by d positive definite variance matrix, okay. Can't have no zeros and stuff in there, okay. No zero eigenvalues, I should say. So we have that, okay. And the density function is this mess over here, but there's a lot of kind of parallels between the density function of the multivariate normal and the univariate density function, okay? So you have the same square root 2 pi, except this is 2 pi raised to the d dimension, okay? The variance, we have the variance matrix here, and that shows up here, except it's the determinant of that variance matrix, okay? And then you have e raised to the, okay? And instead of x minus mu squared, you're going to have x minus mu transpose times x minus mu, our vector x minus mu transpose times our vector x minus mu. And that's like the matrix version of x minus mu squared, right? It's like squaring is you take the vector transpose times itself, and you basically get that. And then instead of dividing by the variance sigma squared, you're multiplying by the inverse of the variance matrix, which again in linear algebra there's no dividing by a matrix, but you do have multiplying by the inverse, which is kind of this conceptual extension of like division, I guess, but yeah, multiplying by the inverse. So there's definitely like parallels if going from the univariate scalar value case to the multivariate vector case, right? And then the over 2, that's included in the -1/2. Okay. All right. Oh, and then just kind of the geometric interpretation, so here we have the determinant. Determinant is the area of the, I guess, the parallelogram of the vectors in sigma, or if you have a higher dimensional thing, it draws out like a parallelepiped. Is that what it's called? I don't know, right? Parallel prism thing, or in hyperprism, I guess, and it's whatever volume is there. Okay, and basically this is here just to make sure everything integrates to 1. Okay, this is just some arbitrary constant so that the whole thing integrates to 1. Okay, so here's an example, and if you have a diagonal variance matrix, okay, then the diagonal variance matrix means there's no covariance terms and everything is just independent of each other, right? So x1 is independent of x2, which is independent of x3 because we have no covariance terms. So that means we can just factor the whole thing out into 3 separate univariate densities, okay? So here I've got basically my mean vector, everything is centered at 0. My variance matrix is the identity matrix in 3 dimensions. And so if I were to do this, okay, X transpose times the identity matrix, the inverse of the identity matrix is the identity matrix. So X transpose I times X just becomes basically x1 squared, x2 squared, and x3 squared, the sum of those things. And, because of e raised to a sum is the product of these things, this will just factor into, I got a standard normal for x1 times a standard normal of x2 and standard normal of x3. And so our density function is just the product of 3 independent standard normal densities. Okay, and so whatever values you have here, we just kind of take the product of them, and that would be our joint density. Okay, so our joint density over 3 things is going to be small, and that's So that, I guess that's another thing you have to just kind of be concerned about. The examples that I'll give you in your homework will be reasonably sized, but if you have a high dimensional, really with any high dimensional probability density, but also with the normal density, you could run into underflow errors, or just run up against floating point precision, just because you're going to be dealing with really small numbers. And so dealing with log probabilities instead can help alleviate that. Okay, but anyway, this is what we have there. Any kind of diagonal matrix, if your density, if your variance matrix is diagonal, then it can always be factored out into just a product of independent univariate distributions. Okay, because if your variance matrix looks like this, then your inverse is just going to be 1 over sigma. Basically everything else will be 0, and you'll just have 1 over sigma 1 squared, 1 over sigma 2 squared down your diagonal. And so these would be your variance, your precision terms, and everything else is 0. Okay, and then so when you expand out your multivariate distribution, multivariate normal distribution, you'll have all of these x minus mu's. Okay, but again, they still just factor out, right? And so you can just have a product of univariate normal densities. So even if it's not the standard normal, it's still just going to be a normal distribution, univariate normal distribution here times a univariate normal distribution for each of these terms. And so this plays a role. Later on, we'll have what we call the naive Bayes classifier. And in the naive Bayes classifier, we assume all of our predictors are independent, and so we can take advantage of this property. Okay, it's just a product of the PDFs of normal distributions. Okay, but in a lot of cases, we don't have independent predictors. So here I've got a 3-dimensional normal distribution, and I've got a mean vector here, and this is our variance matrix. Okay, so down the diagonal is my variance. So I've got so if you just look at the diagonal terms, that will give you kind of your marginal distribution. Like if you just looked at the distribution of x1, it would have mean 1 and variance 4, or standard deviation 2. If you looked at just the distribution of x2, it would have mean -1 and variance 1. And for the distribution of x3, you would have mean 2 and variance 9. Okay, so just going down the diagonal, you get all of those individual terms. Okay, and then you will have the covariance terms. The covariance between x1 and x2 is going to be just this term. You have a covariance of 2. The covariance between x1 and x3 is 0, which means x1 and x3 are independent of each other. Okay, and the covariance between x2 and x3 is -1. Okay, and that's possible. You can have so x2 has covariance with x1 and x2 has covariance with x3, and that's fine. But x1 and x3 are independent of each other, and that's also okay. It's kind of like, what's an example? Okay. Let's say you have two people ride the bus, or they commute to work by first driving to the bus station or walking to the bus station, and then they ride the bus to work. Okay, so if you look at the covariance, or the covariance between the total commute time, between I guess person A and person B, there's going to be covariance between them, okay, because they have that bus ride in common. And then, but, I guess, and then if you look at the bus ride, the bus ride itself, like how much time they spend on the bus for person one and person two, obviously that's going to be, it's like the same variable, so it's highly correlated there. But then if you have the term for how long did they spend commuting not to the bus, so this, person A walked and person 3 drove in or whatever, those values are going to be independent of each other, okay? So the amount of time they get to the bus to get to the bus station is independent. The total amount of time they spend together commuting, the total commute time will have covariance. The amount spent on the bus will have covariance, obviously. But yeah, the amount not going on the bus together will be independent. So you can have things that are like the total commute time, it wouldn't be negative, but it would be correlated to everything. Whereas, how much you have, is independent, right? The total commute time, like if the person walking had a long walk, their total commute time will be correlated with how long they walked. The person driving, if their drive took a long time, their total commute time will be related to that. If the bus ride was really long, their total commute time will be related to that. But the walk time and the drive time will be independent of each other. So you can have things like that, and yeah, stuff like this. Well, anyway, so you can kind of take these subsets of the covariance vector, and that would also reflect, like if you only looked at x1 and x2, it would, a subset of that would be the multivariate normal distribution with this variance matrix, and this 1 and -1 as our mean vector there. Okay. Oh yeah. So subsets of x also follow the multivariate normal. So if we were to just look at x1 and x3, then we would have this normal distribution, and x1 and x3 would be independent, and you'd have covariance 4 and 9. Okay. If you have some matrix C multiplied by your predictor, by your values x, okay? So x has a multivariate normal distribution, and you have some matrix C, okay? So that, your y's are going to be, a linear combination of your x values, okay? Then you can calculate the mean and variance of y by using this, okay? So the mean will just be C times mu, and I think that makes sense. And then the resulting variance will be basically the covariance, C, basically C squared, but, C sigma C transpose. So for example, you could say x has this multivariate normal distribution, okay? And then y is going to be x1 plus x2, and it will also be x1 minus x2. Okay, so we have y as a linear combination of these things. So how do we, what is the corresponding C to illustrate this? Okay, C would be 1 and 1 in our top to reflect that we're taking x1 and x2. So basically just the, I guess the weights here is just 1 x1 and 1 x2 being added together. And then down here we have an x1 and a negative x2. So we'll have a 1 and a negative 1 for our C here. Okay. And so, if we do C times x, we get exactly what we would have, x1 and x2 and x1 minus x2. So if our mean values for x are 1 and 2, our expected values for y will be 3, and 1 plus 2 is 3, and then 1 minus 2, negative 1. That makes sense for our expected values for y, okay? But what about the variance, okay? x1 and x2 are independent of each other, okay? But if y is going to be x1 plus x2 and x1 minus x2, then the resulting matrix will have, or the resulting variance, there will actually be some negative covariance between these two things. And so the resulting variance of x1 and x2 will be, that makes sense, 1 plus 3, you get 4. So, we're just doing C times sigma times C transpose, okay? And so, resulting variance of x1 and x2 will be 4. Resulting variance of x1 minus x2 will also be 4 because variance is additive. But then the covariance between these things, even though x1 and x2 themselves are independent, y1 and y2 will have negative covariance, okay? And that actually kind of makes sense, because if you have a large value for x1 plus x2, okay, we would expect x1 minus x2 to be kind of smaller. And on the other hand, if the sum of these things end up, on the smaller side, we could expect the difference between them to end up being kind of larger. Just on the, if you think about like what x1 and x2 can be if they're similar in size, versus if they're, one is vastly positive and the other one's vastly negative or something like that. Okay. And this is, I guess, just kind of a derivation of that. Showing that relationship. So if you wanted to calculate the derivation, or I guess the derivation of what's the variance on this, you can go through this, and so that's that. But this is just kind of an example there. All right. Your last two view quiz answers are B and E. B and E. All right. So we'll wrap things up here. Again, this establishes kind of a base for what we will look at next week. So next week we'll start doing some classification methods and I guess a little bit more machine learning stuff there. All right, so have a great weekend and we'll see you next week.